speaker is Ya-Wen Sun from University of Chinese Academy of Science. So today she's going to talk about topological mode in relativistic hydrodynamics, so which sounds very interesting. So let's welcome Ya-Wen and enjoy her talk. So please, Ya-Wen, go ahead.
Hi, thank you. Uh, I would like to thank the organizers for inviting me to this conference for the second time. So this year we cannot go to Pohang, but I'm still very happy to see all of you through this video conference. My talk today is about how to produce topologically non-trivial gapless modes in relativistic hydrodynamics and about its holographic realization. This talk is based on two of my recent papers on arXiv in collaboration with Yan Liu. So I will first start from the introduction of relativistic hydrodynamics. So we know that hydrodynamics is a very universal description of a system close to its thermal equilibrium. So when a system is perturbed slightly away from its thermal equilibrium, its long wavelength and long time limit will be described by hydrodynamics. Hydrodynamics describes a lot of systems in our universe, like the coagulant plasma, in QCD and wild cell metals, graphenes in condensed matter systems. And the dynamics of hydrodynamics is determined by conservation equations of conserved currents. In the simplest case, when we do not have other internal conserved currents, when there is only one conserved quantity, the energy momentum tensor, in this case, the hydrodynamic equation of motion would be the conservation equation of T mu nu. And making use of these constitutive equations, we could solve the system when we perturb it from equilibrium. So in 3+1 dimensions, relativistic hydrodynamics have...
So you're now describing the hydrodynamics in a flat space-time or?
Oh, yeah, in the Euro sense. For the flat space-time, yeah.
Okay, thank you.
So in 3+1 dimensions, when we only consider the perturbation of T mu nu, we have four modes. Two of them are propagating modes, which have a dispersion relation like this, and it's also the sound mode. And two of them are the diffusive modes, which have the dispersion relation like this. So we know that, so for hydrodynamics, we know that it describes the long wavelength limit, so we can expand the system in derivatives, that is in orders of K and omega. So this is the first order, leading order in K contributions, and this is the second order in K contribution. And these imaginary parts only come from the second order in K contributions. So which means that at the leading order in K, there's no dissipative effect for the modes, and we have a real spectrum. So we will first focus on the leading order in K modes. And in this limit, that is at the first order in K, the spectrum looks like this. So we can plot the omega K spectrum in this way. And we see that these four modes, they cross at omega equals to K equals to 0. This is because of the energy momentum conservation. So now comes the motivation for our work. So this spectrum looks very similar to the spectrum of massless Dirac fermions in a condensed matter system. So in a condensed matter system for massless Dirac fermion, the spectrum looks like this, with only these two bands, and they cross at omega equals to K equals to 0. And we know that for condensed matter system, so for massless Dirac fermion, we could deform the system to get wild cell metals. And wild cell metals are a kind of topologically non-trivial gapless states of matter. So I think most of you might not be familiar with this. I will explain a few more words on what is a wild cell metal here. So we know that this is the spectrum of a massless Dirac fermion, and this is the gapless node, the Carson node. And this node could be could easily be gapped. That is, a gap will open here and there will be no crossing anymore just by introducing a mass term in the Dirac equation. So this is simple and it will become a gapped spectrum. And then if we introduce some time reversal symmetry breaking term in the Dirac Hamiltonian, then this crossing node will be separated into two crossing nodes like this one. And in this case, if we still add a mass term to this system, these two nodes will not be gapped. And there's only a gap here and here. So in this way, these two crossing nodes are called topologically protected nodes because they will not be easily gapped with the mass term. And they have non-trivial topological charges, +1 and -1 for each of them. And only when the mass gap, the mass term is very, very large, so the system goes through a topological phase transition to a trivial state. In that case, it can be gapped. So this is called a topologically protected state. So that's what is a Wowson metal. So now, because we see that from this standard hydrodynamics, the spectrum of these 3+1 dimensional hydrodynamic modes looks very similar to a massless Dirac fermion. So our question is if we could also deform this system to get topologically non-trivial gapped states of matter like a Wowson metal. And there have been a lot of work on this kind of classical topological states of matter for like topological sounds, topological optics. So here we want to try to find similar classical topological states of matter from relativistic hydrodynamics. And also because there are a lot of experimental realizations of relativistic hydrodynamic system. So we want to see if we could also observe this effect from experiments. And we also want to know if this has implications to other topological systems too. So this is the motivation of my work. So here the outline also is the main storyline of my talk. For our goal to find the topologically non-trivial gapped states of matter, the first thing is to deform the system. And an easy way to do this is to first define an effective Hamiltonian of the system, which plays a similar role to the Hamiltonian of a fermionic system. And just from the spectrum of this Hamiltonian, we will see whether they are cousin nodes or not. So we will first define an effective Hamiltonian for relativistic hydrodynamics, and this is only for our computational convenience. And after having this Hamiltonian, we will try to modify it to make it gapped first, like what I told about this Wowson metal story, and then try to separate the crossing nodes to more nodes which might be topologically protected. And then I found that we will find that this could be done, but the Hamiltonian needs to be modified. But we know that from the standard hydrodynamics, the form of the Hamiltonian is fixed. So when we modify the Hamiltonian, we need to change something of the system. So the easiest way is to change the conservation equation. That means T mu is not conserved anymore. So in this case, we could produce the terms that we need to modify this Hamiltonian. But there's a related question, that is, how could these terms arise? So why should the energy momentum tensor become non-conserved, and what caused this non-conservation? And our answer is that it can be caused by a gravitational field, a very small gravitational field. And this gravitational field could be produced by a coordinate transformation from an inertial reference frame to a non-inertial reference frame. So this, in principle, this could be tested in experiments. So these first three parts are the main message that I want to deliver in this talk. So after this, I will introduce some related properties of the system, like the transport behavior, the higher order in-K effects, and how to prove that they are topologically protected. We need to calculate the topological invariance, and we can generalize the system to more complicated ones, and how to realize them also in holography. And finally, I will introduce some open questions. Yeah. So let me come to the first part to define an effective Hamiltonian for the system. So the conservation equation for hydrodynamic system looks like this. And this delta T mu is the perturbation of the energy momentum tensor away from the equilibrium. And so making use of these constitutive equations, we can express these components of this delta T mu using these four variables. And we can define a vector, which is the combination of these four components. And when we define a vector like this, this conserved equation of motion could be written into this form. So this is a vector equation of motion. Psi is a vector. So in this way, H becomes a matrix. And from these equations, we can write H like this. So this matrix is this H. And so this is very similar to what we have for a Dirac fermion. For Dirac fermion, this psi is a spinor. In 4 dimensions, it also has 4 components. And in this way, this H Dirac Hamiltonian is also a matrix. And also similar to the fermionic case, the eigenvalues of this H would give the spectrum of the hydrodynamic modes. So there's one thing here. So in quantum mechanics, when we want to have a real eigenvalues, we need H to be Hermitian. And here, apparently it's not Hermitian because of this with S squared, but it's very close to being Hermitian. So we can see that H is similar to a Hermitian matrix just by a transformation like this. So in the following, we will also focus on effective Hamiltonians, which are Hermitian or similar to Hermitian matrices. In this way, we will get real eigenvalues. So we do not have dissipative effects at leading order in K. And in the following, we will first focus on leading order in K effects. And afterwards, we will introduce K squared terms. So now we only have this leading order in K.
Ya-Wen, may I ask a question in the previous page?
Yeah.
I'm just trying to match your equations here. In the psi, you have a pi x, pi y, and pi z.
Yeah.
And in the equations, you have pi parallel and pi perp.
Oh, yeah. So this is because we choose this system to only have a non-zero kx. So this is a simplified version of the equations of motion. So this pi I, it means pi y and pi z. But if we restore all k's, it should be like this.
Right. So then this I is y or z.
Yeah, exactly.
And what do you mean by this parallel and perp?
Oh, this is because we choose the momentum to be in the x direction.
Oh, x direction. Oh, I see. Now I got it. Yeah, okay. Thank you. Yes.
This is a simplified version. In fact, we need to restore our case. Yeah, so this is different from the Euro convention in the literature.
Okay, thank you.
And so now from this spectrum of this effective Hamiltonian, we could get this leading order in K spectrum, which is the same as we had here. And now the spectrum looks like this. So now we have defined this effective Hamiltonian for a relativistic hydrodynamic system. So the next thing we want to do is to modify it to have to try to find the topologically non-trivial states of matter. As I mentioned for the Wild-Sam metal case, the first thing we need to do is to gap these nodes to make this gapped. And then we need to separate this node to 2 or more nodes and to prove that they will not be gapped by the mass term that we introduced. So now we come to the first step to gap the hydrodynamic modes. So we will just modify this effective Hamiltonian and see what kind of modification would give a gapped spectrum like this. So at this stage, we add all terms, add extra modifications by hand, but later we will show how they could arise. But now it's only very artificial. So we found that if we add two terms here, they will play the role of a mass. So if we modify the effective Hamiltonian in this way, with these two extra terms, and this effective, the final spectrum will look like this. And this it's gapped. And we can see that these two sound modes are gapped, but the diffusive modes do not change. And here we add this mass term in the x direction. We could also add them in the y or z directions, and all of them are the same. And we have also chosen the order of m to be of order k. That is, the energy momentum tensor is not conserved, but it's only broken very weakly. So it's still within the hydrodynamic limit. So within my talk, all the parameters will be at the same order of k. So it's the hydrodynamic limit. So after gapping this system, so here there's one thing that we need to note that. So there have been a lot of work in adding momentum dissipations in holography and also in hydrodynamics. So there, they also have modifications to this energy momentum conservation equation. So they introduced the non-conservations, but that is different from what we have here. So here we have this, if we write it out in terms of these equations, we will find the equation is modified in this way. The y and z directions are still conserved, but the energy density and the s direction momentum are not conserved. And the non-conservation is proportional to each other. And there's an opposite sign here. But for momentum dissipation, the energy density is conserved, but the momentum is not conserved, and with the gamma here. And from the name, we know this is dissipation. So this means even at a leading order in K, it produces an imaginary part in the spectrum. So this one, the spectrum, this gamma is like this. So we can see that this matrix is non-Hermitian, very apparently. But here, with this term that we introduced as a gap term, the effective Hamiltonian is still Hermitian, or similar to Hermitian matrix. And this spectrum would give imaginary part for this omega. So it introduces dissipative terms, so which we call them momentum dissipation. But this doesn't introduce dissipative terms or imaginary parts. The spectrum is still real. So they are very different kinds of non-conservation of energy momentum tensor. So after gapping this system, the second step is to modify this effective Hamiltonian and introduce more terms. And these more terms could separate the one crossing node to more crossing nodes, which exist even with the presence of the mass term, very similar to Lao's metal. And we found that if we modify the effective Hamiltonian in this way, so these B terms are still Hermitian or similar to Hermitian, and they are in the y and z directions. If we introduce them in this way, and the mass term in x direction in this way, the spectrum would look like this. We see that there are now 4 crossing nodes, and these crossing nodes exist for non-zero m. We can see from this spectrum that compared to the gapped one, we can see that these two sound modes do not change, but these two diffusive modes, one goes up and the other goes down and becomes this one. And this distance between these two original diffusive modes becomes B. And this distance between the two original sound modes is now M. So we can see that when B is larger than M, there will be 4 crossings. And when B is smaller than M, the system would be fully gapped. There will be no gapless crossings. So this is the main message that we have. So now we have modified the effective Hamiltonian of the hydrodynamic system, and we can produce the spectrum which have gapless nodes even with the presence of a mass term. And this is the spectrum which is apparently real. And so there are a lot of remarks here. So first, with this effective Hamiltonian, the non-conservation equation becomes like this. And B and M, they are both of order K. And so all of the components are not conserved now. And then, so after our work appeared on Archive, Professor Karl Landsteiner from IFT wrote to me and told me that very similar modifications in this hydrodynamics have also been found in a non-relativistic hydrodynamic system in geophysics when they study atmospheric waves. It's very interesting. They are working in a very totally different framework, but we have very similar spectrum, but also still different. And they focus on the gapped case. And here we are focusing on the gapless case. And then there's an important remark here is that here we choose the mass term to be in the x direction. But we choose it if we choose it also in the y and z directions. So there, if the mass term is in the same direction as this B term, the system would still be gapped. The spectrum would look like this, and it's fully gapped. There will be no band crossings. So this means that these crossing nodes, they are only topological when there are no mass terms here or here. So this means that these are topologically non-trivial. These crossing nodes are only topologically non-trivial, protected by certain symmetries. These symmetries are the symmetries that forbid the mass terms in y or z directions. So this is an illustration showing what is topological and accidental crossing. So for those who are not familiar with these concepts in condensed matter physics, so when we say this crossing is topologically protected, this means that a small perturbation will not gap it. So this crossing would always exist when you perturb the system a little. But when a crossing node is accidental, is an accidental one, it's not topologically protected, or we say it is topologically trivial, it means that a small perturbation would open this gap. So we can easily see from these two figures, this one is accidental and this one is topologically protected, because this is a band and this is a band, and a small perturbation would only change the position of the two bands relatively. So the crossing is always there, just the separation between the two nodes would change a little bit. And for symmetry protected topologically crossing nodes, we mean it can be gapped by some terms. But when they have a symmetry, when we have a symmetry that forbids these terms, the system would still be topologically protected. So this is the case here. And we can see that when we change the two parameters B or M, the system would develop this a topologically phase transition. When B is larger than M, we have 4 crossing nodes, And when B is equal to M, we have only 2. This is the critical point. So at this critical point, when you perturb more, when you have B smaller than M, the system would become fully gapped. And this figure is for non-zero KY. So this is at 0 KY and KZ. This is for non-zero KY. This means, so this is only a figure for us to see the whole picture in the full KS, KY, omega, the 3-dimensional space. So this means that in the 3-dimensional space, these 4 crossing nodes are 4 points, but not circles or lines. So they are dimensional 0 objects. So this is only for this assistance to see this point. Up to now, so let me summarize a little bit what we have done now. So I have seen that for relativistic hydrodynamics, there are hydrodynamic modes, four hydrodynamic modes in 3+1 dimensions, and they have a crossing at omega is equal to k equals to 0. And then if we modify this hydrodynamics to make it weakly non-conserved, we could modify the spectrum into this kind, and we will see that the system could become so the system would become a topologically non-trivial gapless system from this topologically trivial one. And here we have emphasized that it has to be symmetry protected. So this is what we have up to now. And then the next question is, so this modification to this effective Hamiltonian looks quite weird and artificial. So how could these terms arise? So it's very similar to what we have for momentum dissipation. When we weakly break the translational symmetry of the system, we would have a similar effect. And in that case, in the case of momentum dissipation, we could use an external scalar field, an external vector field, or tensor field, which could all have a very similar effect to break the translational symmetry. But here, the terms are very fine-tuned. In this way, we could only use an external tensor field. So scalar fields or vector fields could not introduce non-conservation terms like that. And only a symmetric tensor external field could play this role. So we introduce a symmetric tensor external field, which couples to this system. And it's an external field. So the system, the momentum, the energy momentum of this system will not be conserved due to this external field, due to the interaction with this external field. So it has energy momentum communication with this external field. And the non-conservation equation looks like this. And compared to what we need to have for these 4 equations. So here we need to choose O to be also T mu nu. So if we choose this operator O to be T mu nu, and we carefully choose non-zero components of F mu nu, we could, in principle, get non-conservation equations like this. And in this way, we could produce spectrum like this and get what we want. So now, what is this F mu nu? Because it has to couple to T mu nu. It could be an effective coupling when F mu nu is an effective external matter field, but that is very complicated because the interaction needs to be fine-tuned. And now there's a very, very natural quantity that could couple to T mu nu of the system, which we know is the graviton. So there's a very interesting and natural possibility for this symmetric tensor F mu nu, which is to be the gravitational field. So we could introduce a gravitational field. So note that because we need the energy momentum tensor to be non-conserved only weakly. So to be weakly broken, so this gravitational field should only deviate a little from the flat spacetime. So this h mu nu is of order of k2. So when we have a curved spacetime, so here, note that we have not introduced holography yet. So it's still relativistic hydrodynamics. There's no holography. So here the gravity is the gravity which couples to the relativistic hydrodynamic system. And this T mu nu. So we know that when there's a non-trivial gravitational field, the energy momentum tensor is only conserved covariantly. We need this nabla mu T mu nu is equal to 0, not partial mu T mu nu. So in this way, when h mu nu is a small quantity, we could expand this covariant conservation of energy momentum tensor. And the expansion looks like this. So at the on the left-hand side, we see this partial mu delta T mu nu. And on the right-hand side, we see these terms proportional to this graviton field. And this produce non-conservation terms for this partial mu delta T mu nu. So here it's very similar to what we have here, but a little different with more terms. And so with this, so the logic is very simple. We just introduce a non-trivial gravitational field. And with this non-trivial, very small curved spacetime, with this very small non-trivial gravitational field, the conservation of energy momentum tensor becomes it has also a little deformation from the usual partial mu one. And these extra terms look like this. And very similar to the case here, if we fine tune the components of H, we could get the terms that we need here. And now, in fact, there are many ways to choose the non-zero components of this h mu nu. And we pick a very simple choice. And this is a very simple one. We could just choose all non-zero components of h mu nu to be this. And with this, we substitute this into this equation. We would get the covariant conservation equation in this way. So this gives exactly the terms that we need. So it looks very artificial here. And when we found that these artificial terms could arise from this graviton field, so this it's still a little weird that these terms look very strange, like mx and bvsc. So how do these terms arise? So how can we have this non-trivial graviton field? Surprisingly, so for this G mu nu, eta mu nu plus h mu nu, where h mu nu is like this. So for this time, surprisingly, all Riemann tensors vanish. So this means the spacetime is in fact a flat spacetime. So this h mu nu, they only arise because we have a coordinate transformation from the flat spacetime to a non-trivial one. So they are diffeomorphism, they are asymmetric, so they can be associated with each other by a coordinate transformation. And we could work out the coordinate transformation that we need from the expression of this h mu nu. And the coordinate transformation looks like this way. So up to this stage, we have transformed this strange behavior of these extra terms into a special coordinate transformation. And so this means that in a specific non-inertial frame, because we have a non-trivial coordinate transformation, and the metric is not the flat one, but the spacetime is still the flat spacetime. So this means we are now observing in a special non-inertial reference frame. So this means that in a special non-reference frame, we could observe hydrodynamic modes that are topologically protected, even when they are topologically trivial in the original inertial frame. So this is another effect for accelerating frames, in addition to the very famous, well-known ONRA effect for accelerating observers.
Excuse me, may I ask a question?
Yeah.
So here you consider non-inertial frame. So in this new coordinate system, how to define the energy and the momentum?
This energy and momentum.
Because maybe in this new non-inertial frame, the T tilde is not the, I mean, the energy from the observer in this inertial frame. That's possible?
So yeah, this energy momentum has to be the energy momentum defined for this new diminutive.
Observer.
Yeah.
Yeah.
It's not the one for it menu. So it's the one for menu. It could also come from a coordinate transformation from the original one, or you can just.
I agree, but in this non-inertial, I mean, coordinate, you choose the T tilde component in your non-conserved, I mean, the expression for the, I mean, for the conserved law, I mean, non-conserved law, but the T, I mean, capital T hat T tilde, this quantity is not the energy observed in this new frame.
Yeah. So in this new frame, we use this T menu that has to be covariantly conserved. So it has to be the T menu defined in the metric J menu. When you use T naught, for example, T naught is not the energy density observed for it menu. That's true. But that doesn't change the hydrodynamic mode. So what we observe here is not the energy density or momentum density, but the hydrodynamic modes. So for the hydrodynamic modes, we don't care what you observe, like T naught or T menu. We only see what we observe for the hydrodynamic modes.
So you are only interested in the dispersion relations like this?
Oh, yeah, dispersion relations. So that doesn't matter.
Okay. So okay, maybe you can continue. We can talk later after your talk. Yeah.
It's very noisy. So now the last step is to see what this coordinate transformation corresponds to. So what is this special non-inertial frame? So this can be found just from this coordinate transformation. And we see what is a rest observer in the new reference frame. For a rest observer in the new reference frame, it has to have this dxi tilde equal to 0 for the spatial directions. And solving this equation, we could find this special non-inertial reference frame. And we find that so observed in the original flat spacetime, in the original inertial frame, this rest observer in the non-inertial reference frame would move in this way, and we integrate these movements, and we will find that in the x direction, it is accelerating constantly. So this is the x direction. So it has like x equal to 1/2 AT². So A is the acceleration, and it's a constant here. And in the y and z directions, it is rotating at a constant angular velocity. And this is y and z direction integrated. And these are not is the radius of the rotation, and it's arbitrary. And this also because at order k, this b and m's are of order k. So this means that they are moving in a non-relativistic limit, very slow motion. So here is a figure showing this non-inertial reference frame. So the observer that is observing these topological modes of hydrodynamics, they're rotating this way, and they are rotating in these y and z directions, and at the same time accelerating in the x directions, and they are moving in a helix in this way. With a constant angular velocity and a constant acceleration in the x direction. So up to now, we have found that in a special non-reference frame, we have this. In a special non-inertial reference frame for this special accelerating observer, he could observe topologically non-trivial topological states of matter, which were topologically trivial in the original inertial reference frame. So this is another testable feature for accelerating observers in addition to this Unruh effect. And there's also a remark here. So with the coordinate transformation to this new frame, with this, the conservation equation changed because of the coupling to H mu nu, but the constitutive equation has also has to change. And in the previous calculations, we have not taken into account these changes, but we have to add them. And after adding them, we found that these contributions all vanish or cancel each other. And finally, the spectrum is just this one. And there's no modification from the constitutive equations. So this is very interesting. So note that here, we have this observer accelerating this way, but the fluid, the relativistic hydrodynamic system, is still at rest in the inertial frame. So it's related to what Lily asked just now. So the energy momentum tensor is still the original flat space one transformed into this new non-inertial reference frame. And so everything this accelerating observer observes could be seen as a coordinate transformation from the original frame. We could also consider the case that the observer and the fluid, the relativistic hydrodynamic system, both of them are accelerating. And in this case, we could also find a similar spectrum. There's only, but in this case, the constitutive equations have contributions. But the contribution only rescale these parameters M, E, and Vs. So the qualitative behavior of the spectrum is the same. It's still like this. So we have found that the observer has to accelerate, and the hydrodynamic system could stay at rest or could also accelerate in the same way. And the results are qualitatively the same. So now we have shown that, so as I mentioned earlier, the system, it's only topologically protected with a symmetry that forbids the mass term in the y and z directions. That is, it only allows a mass term in the x direction. So we need to work out the symmetry of the system. So what is the symmetry? And so the easiest way to work out the symmetry of this new system is to get the isometry of the new metric J mu nu. So the isometry of this J mu nu is just the symmetry of this modified hydrodynamic system. There are two ways to solve for this isometry. One is just to solve the killing vectors for this new metric J mu nu. And the other way is to also transform the original killing vector, that is the generators, the 10 generators of the Poincare symmetry, 4 translational ones and 6 Lorentz ones, to transform them by coordinate transformation to this new reference frame, and they both give the same results. And finally, we have these 10 generators of the symmetry, and the 4 are related to the original translation symmetry, and these 6 are the original Lorentz symmetry. And the symmetry that we need to protect the system are Chi1 and Chi-Z. It looks strange. In fact, we can see this generator, this killing vector is a combination of translational symmetry and a booster symmetry in the Y and Z directions. But in fact, these 2 symmetries are just the coordinate transformed version of the original Y and Z translational symmetry. So this means that for the system so when we observe from the inertial frame, if the system have a translational symmetry in Y and Z directions, so observed by this accelerating observer, he will observe a symmetry that protects this, that forbids this mass term in the Y and Z directions. So this is the symmetry that we need. So this means that observed in this new non-inertial reference frame, the symmetry looks like this. But observed in the original inertial reference frame, the symmetry are just the Y and Z translational symmetries. So this we could easily do in experiments. So here is a summary of the main message of my talk. So we start from the standard relativistic hydrodynamics. We have 4 modes. And then we want to deform this standard hydrodynamics. We break the conservation of energy momentum tensor. We have some extra terms which change this topologically trivial gaseous modes into topologically non-trivial gaseous modes, but with the protection of certain symmetry. And we found that these extra terms could in fact come from a coordinate transformation from an inertial reference frame to a special non-inertial reference frame observed by an accelerating observer moving in a helix. This is very easy to realize in experiments, and this brings up an interesting observational effect for accelerating observers, in addition to the well-known Uran effect. So this is the main message of my talk today. So for experimental realizations, one possible application is the doubling of amplitudes at a finite k and omega, and it's stable under probation. So this might be useful for applications. And this can be checked at laboratories if we accelerate the detector, and we can detect sound modes. We have to accelerate the detector in a helix with the constant acceleration and angular velocity, and then we could detect this topologically non-trivial modes. And this also, an interesting implication is that, so for hydrodynamic modes, when we observe them in a non-inertial reference frame, we will get this non-trivial topological states from topologically trivial states. So what happens for electronic systems? So there have been, so electronic systems, so topological states of matter for electronic systems have been studied extensively during the last decades. If we can realize this topologically non-trivial electronic states of matter also from this mechanical ways, by accelerating observers or by accelerating the materials, that will be very interesting. And we have also had some preliminary results in this aspect. So because of the time limit, I will go through very fast the rest of the part of the talk. So first we need to show that this mode is indeed topologically non-trivial. So we have to show that a small perturbation cannot gap them. So usually we define topological invariant. A topological invariant means that if this could be easily gapped, there should be some quantity which could be 0. So if this system is topologically non-trivial, this same quantity should be non-zero for this system. So this is usually a topological invariant means. And here it's very easy. We could just compare these two states, eigenstates near the crossing node. So for the same band, for example, the orange band on the left of this node and on the right of this node, if these two states are orthogonal to each other, it will mean that a small perturbation cannot gap them. Because if a small perturbation could gap this orange band would separate from this blue band. So this crossing point, at the crossing point, the left limit and the right limit has to be the same state. But here they are orthogonal states. So this means that there should be a singular point in between these two states. So it has to be a topologically non-trivial crossing node. So here is the main logic here, but I will not show the details. So we have shown that this is indeed topologically non-trivial, but protected by symmetries. And we also calculated the transport, the second order effects. I will skip the details. And this is the second order in K effects. This gives the imaginary part. That is a deceptive effect for the system. So this is the real part, and this is the imaginary part with K-squared fractions. So for the same band, the real part has a crossing here, this orange band and this blue band. So this orange band is the real part of this orange band is continuous here. But here, there's a jump in the imaginary part of the orange band. So this provides another piece of evidence that there's something happening here. So it's topologically it's a singular point. The imaginary part is not continuous, and the states are not continuous. They are orthogonal to each other. So this is very consistent with the calculation of topological invariance. And also this holographic realization. I will also skip the details here. So we need to introduce non-conservation of energy momentum tensor in holography to produce this system. And usually this is realized by method gravity. But here we also choose a simple way, that is to have a holographic version of non-inertial reference frame. So we have this original adiabatic correspondence, and then start from it and perform a coordinate transformation, the same coordinate transformation to a holographic version of non-inertial reference frame. And we developed a new prescription for calculating the word identities for T mu to show that this T mu indeed is non-conserved in the way that we require. And what we are doing now is to work out the hydrodynamic modes directly from holography to prove this, and this is still work in progress. And we also generalize these systems to more complicated ones. And I will just also skip them. So finally, this is the summary. So we get gapless topological modes in relativistic hydrodynamics by adding extra terms in the effective Hamiltonian, and these extra terms could be produced by a special coordinate transformation from the flat space from the original inertial frame. And so the main message that I want to deliver is that topologically trivial modes could become symmetry protected topologically non-trivial gapless modes in a certain non-inertial reference frame, which is the frame of an accelerating observer moving in helix. And this could in principle be tested in laboratories, and this brings a new effect for accelerating observers in addition to the famous aura effect. So here are there are many open questions. So what we are doing now is to add an external U1 and internal U1 current. So when the system has more conserved currents and with more modes, there will be more complicated topological structure. And also we are working on the holographic calculation of hydrodynamic modes. And so this is related to the PT symmetry protected non-permission quantum mechanics. So here, because we also have a non-permission effective Hamiltonian, but whose eigenvalue gives real spectrum. So we want to we try to find if this is related to this PT non-permission physics. And also another thing that we are working on is to see for if non-inertial reference frames also produce non-trivial fermionic topological states of matter. And further open questions include if we could find gapped topological modes or gapless modes with other kinds of topology and more complicated system mode transports, and to realize them in experiments, and also for non-relative state systems. And also, besides this holographic realization by just performing a coordinate transformation, could we also realize them just from massive gravity? And for the generalized systems, could we also find similar physics and the relation to gravitational waves? Yeah, thank you. That's the end of my talk.
Okay, thank you for a very nice answer. Yes. No, that is not your problem. So, do we have any other questions or comments? So, while people think, let me ask you one question. So, at some stage, you showed us some transports of this system. So, what is the characteristic property of some transports from this theory?
So sorry, let me close the window. So noisy. So you mean the transport part? This?
Yes.
So what was your question?
So what is the characteristic property of this transport from this theory?
Oh, so so this I didn't really introduce in my talk. So so for this system, because we only have this thermal conductivity, because we only have this two minutes, we only calculated this thermal conductivity, and they have several components. And for this original standard hydrodynamics, they only have non-zero kappa xx, kappa yy, kappa zz, and they have zero yz, zy because of the time reversal symmetry. And here, our B terms break this time reversal symmetry. So this original zero components become non-zero now, but still finite. And this original infinite conductivities now become finite due to these M terms and also B terms. This is because from here. So for standard relativity hydrodynamics, there is a crossing here at omega equals to k equals to 0 due to energy momentum conservation. So this produces an infinity in these two thermal conductivities. But now with our mass here, it's gapped. So these two quantities become finite. So
Okay, then may I understand, because of your new two parameter MMB, these thermal conductivity could be finite instead of infinite, right?
Yeah. And this become non-zero.
Okay,
because
I see.
of the symmetry breaking.
Okay. Any other questions or comments?
Okay, I have a question. So,
Yes.
to make sure, so do you mean you measure the same system but using a non-inertial observer, correct?
Yeah.
So the same system but observed by a non-inertial observer. So,
Yeah, exactly.
so for this non-inertial observer, how to define the frequency and wave number for this observer? Because you talk about the dispersion relation for associated with this observer. So how to define the frequency and the wave number?
Yes. So
Okay.
the frequency and so it's like so you don't know you are a non-inertial observer, right? So you observe something and you expand the system in Fourier transformations into the k and omega space. So this k, so the original k is different from the k you observed. So a plane wave in the original inertial frame would become a combination of a wide spectrum of plane waves with different k's and omegas. But you can still define your own k and omega just by Fourier transformation, right? So indeed, omega are different from the original ones, but you can define them from the physical quantity that you observe. You can measure your own k and omega in your own frame.
You mean even for a non-inertial observer?
It's not a plane wave anymore, usually.
Yeah, that's
So,
my point. So it's not a plane wave. So can you always do this?
so you always have plane waves in your frame, but
Yes.
it's not the same plane wave from the original frame. So a plane wave in this room is not in this frame is not a plane wave in that frame, but in both frames they have their own plane waves, right? So they can define their own k.
Oh yeah, maybe. So okay. So the next question. So I'm a little confused with the conserved law. We know the conserved law is a covariant quantity expression. So why you can break the conserved law by just using a coordinate transformation? It's a conserved quantity. So it should be covariant. So just from a coordinate transformation. So I'm confused.
Not really broken. It's like covariantly conserved, right? It's like, for example, in a non-inertial reference frame, an original constant, original object who's at rest now becomes accelerating. Because from the Newton's law, it has to have virtual force. It's very similar. So this part looks like some virtual forces produced by this metric.
Okay.
So in this, for example, in my system, this includes the Carry-Forest force, you know, and the central force, and all of them come from virtual forces.
Okay, I see. So in fact, the law is still conserved, but in a spatial coordinate system, it looks like in some sense break the conserved law like this.
Covariantly, and this difference could be seen as the effect of the virtual forces. So you can see the system in different ways. They are equivalent.
Okay, this is just artificial of the coordinate transformation. So the physics will not change because you see the conserved law is still conserved, no matter which coordinate you choose. Is correct? Okay, I see. Yeah, I just make sure. Yeah. Okay, thank you.
Yes, it's like the Onra effect. The accelerating observers would see very different physics.
Yeah, that might be true. Yeah. Okay, I see.
So then, do we have any other urgent questions?
May I have one short question? What
Yes.
happens? What is the setup in 2 dimension, 2 plus 1 dimension?
Oh, I I didn't try that because
You didn't try.
in this case, we need at least 4 components. So for 3+1 or 4+1 or more dimensions, it definitely works. But for lower dimensions, I'm not sure if we could still find these strange modes, these topologically non-trivial modes, because we need a certain number of modes for them to mix with each other.
But in my opinion, suppose I apply this framework to electronic system. So what I'm thinking is, if I apply magnetic field along z direction, and if I apply electric field along z direction, then automatically I have some setup for accelerating along the.
Do you mean they will accelerate like this?
Yeah, yes. Sorry. So electric field x direction and some electromagnetic magnetic field x direction. The magnetic field plays the role effectively can be, I mean, represented by rotating frame and x electric field applied. Then if I calculate it, for example, in the tight bind mode, maybe I have this kind of some topological band. I'm not sure. So then I want to apply this into the quantum Hall system in 2 dimension. So that's the reason. So in 2 dimension, quantum Hall system hydrodynamics, you know, the people discussed much. So
I know what you mean, but so here, because it's like this. So when you say that you impose this electric field or magnetic field, it means
yes.
the relativistic hydrodynamics I am studying is accelerating. But in my case, the observer is accelerating, but the hydrodynamic system has to stay at rest. And also, I will try to produce these terms. So like these terms, to see if they could arise from a vector field, like an electric magnetic field, but that doesn't work. So that means if I accelerate the relativistic hydrodynamic system while not the observer, it's different. They couldn't produce
I'm
this.
not sure. I mean, magnetic field usually can be rewrite in the space direction is rotating, and I mean, I'm not sure if so. Yeah, but anyway.
It's different at least. So maybe in different systems that could work, but in this system, it's different things. So this one gives a tensor field, but what you mentioned would only give a vector field. So that's very different. The degrees of freedom are different, and to produce these terms, we need a system with more degrees of freedom. So at least in my case, we could only do this using gravitons, not electric magnetic fields. But for electronic systems, that might be very different.
I see. Okay, thank you.
Ya-Wen? Hello?
Hey.
Hi, okay, nice talk. One just a general question is is the fact that the conservation law preserving and the system preserving is the same thing or different thing?
You mean what to consider this conservation of T mu and what?
So you are talking about some maybe a transformation which of the maybe the spectrum, right? Actually, this is this system is just there is no Hamiltonian or Lagrangian specified. It's just hydrodynamics is nothing but just energy momentum conservation.
Yeah.
Right? And especially if there is a mass generated, then It's not anymore hydrodynamic anymore by definition.
Oh, you mean when it's not conserved, is it still hydrodynamics?
No. First of all, two things are different. First of all, there are two separate questions actually. When you generated a mass to the system is no more hydrodynamic. That's the definition, right, of hydrodynamics.
So this is like a weakly broken conservation equation. It's still in the hydrodynamic limit. But of course, if we see that when the system is not conserved, it's not hydrodynamics, it's okay. But we use this.
It's not useful, okay? Because you can still talk about the maybe fluidity and non-fluidity transition, things like that, for which this may be useful. And but I guess that it wasn't very clear to me what this mass generating process really is physically. Well, you were talking about some geophysics, right? But and at the bottom. And in that process, maybe relevant thing is not some accelerated, going to the accelerated system, things like that. Maybe what geophysics matter is maybe just chemical process. So I was a little bit unsure whether you talk about the frame change to talk about the spectrum change or spectrum preservation. So maybe that was one question. And the other one is you were talking about the spectrum protecting symmetry. When you talk about the symmetry, which is protecting the spectrum maybe. And I wasn't sure whether that is a transformation which just leaves the spectral structure invariant, or that transformation is really asymmetry. Symmetry means that Hamiltonian is invariant under that symmetry.
That's different then.
What maybe you just considered is a transformation which can leave this hydrodynamic, spectrum invariant.
So here, by symmetry protected, I mean a symmetry that forbids the perturbation of the system that would get these four nodes. So this symmetry means that when you require this symmetry, the system cannot have perturbations in these y and z directions, the mass terms. So without these terms, this will not get. So this symmetry means the symmetry that forbids the mass terms here. So we'll see if it's something's invariant. So it's like this term is invariant in this symmetry. So this is the second question, right? Does this answer your second question?
So can you show me again what was the actual transformation rule?
You mean this coordinate transformation?
Okay. So is that the claim is that this coordinate transformation is the symmetry, you mean?
This is the coordinate transformation, but the symmetry is the isometry of the new spacetime G mu. It's different. So the new symmetry could also be seen as the Poincare symmetry transformed by this coordinate transformation. So the symmetry are this.
So what is the claim? What is the symmetry?
The symmetry of the new system are the Poincare symmetry of the original spacetime, but they need to be transformed to the new spacetime in this way. But the symmetry that we need to forbid the mass terms in y and z directions are the symmetry, only two of them, the chi1 and the chi-z, only this chi3, only these two.
So what you are saying is chi2 and chi3 is the symmetry that leaves the spectrum invariant?
All of this leave the spectrum invariant.
Oh, all of them.
Yeah, these two forbid the mass term in y direction. So that means these symmetries could be broken. And the system is still topologically non-trivial. But these two should be strictly conserved. Otherwise, the system would be gapped, so they are not topological anymore. So these two are very special in the sense that they would constrain the y and z directions. So these two symmetries are those that we require.
So your system originally was starting from the flat space time, right?
Yeah.
And then this is the coordinated transformation which preserves the spectrum. Isometry?
In the accelerating frame, so in the new frame, this is the coordinate transformation that preserves the spectrum. Yeah, you're right.
Right. So space-time is still flat, right?
Now it's not flat. So now it's this this one, J mu plus this H mu. It's flat, but it's observed in a non-inertial reference frame. So it's not Minkowski this time, but it's equivalent to the Minkowski one. Yeah, there's no curvature in the sense it's flat. But it's not the Minkowski spacetime. It's eta mu plus H mu.
Yeah, I was a little bit confused that the statement of protecting symmetry. That is for usually in topological system, the relevant the symmetry is a discrete symmetry, right?
It's a
which preserves the. So what is the matter is whether the system Hamiltonian is invariant under that particular, I guess, symmetry. So when the Hamiltonian is a symmetric under that transformation, we can say that that particular symmetry is protecting the, I guess, the spectrum.
I see.
You don't have any Hamiltonian, and although you talked about the Hamiltonian, it was not actually Hamiltonian, right? It was you were rewriting the system. I mean the conservation of conservation equation, just as which looks like, I mean.
Yeah. So here there are two concepts of symmetries here. So one is what you mentioned is the symmetry of the system, and like Lorentz symmetry and translational symmetry, Poisson symmetry. And the other is the symmetry in symmetry protected topological states of matter. In that term, symmetry means some symmetry that the system requires to forbid the term, the extra terms which could break the topological structure of the system. So in that case, symmetry means something that you need to have so that the terms that produce a gap would be forbidden. So it's different from the symmetry of the system. It's less than that. So it's smaller than the symmetry of the system.
So could you go to your Hamiltonian, so-called Hamiltonian, previous page? No. Much, yeah. Right there. So can you just go one more page where you introduce the H?
H. You
Yeah.
mean
Yeah.
beginning, this one.
I think so. Right? So here, this H looks like, I mean, some Hamiltonian. It looks like Hamiltonian, but this is not on Hamiltonian, right?
Yeah, it's an effective Hamiltonian. It's different from the Hamiltonian we had for relativistic hydrodynamics.
Not modifying the system, but modifying the structure of a conservation law. To say.
Yeah.
So I'm not sure whether I mean the talking about the isometry or protecting symmetry. I was not very sure what actually is going on, just because.
Question. So you mean that this is not the real Hamiltonian? So the symmetry that protects this Hamiltonian doesn't mean this is the symmetry of the system. Is that your question?
Exactly.
I see. So in my opinion, when we see it's a for example, in this system, we see that the symmetry is a Poincare symmetry. It has a translational symmetry and the Lorentz symmetry. It doesn't mean that the symmetry preserves this one, but it preserves this one. So in our case, we have a nabla mu delta T mu is equal to 0. So in our case, it's the same. The asymmetry is the symmetry that is the isometry, which means the metric doesn't change. When the metric doesn't change, this nabla mu delta T mu, this equation will not change. So what we mean symmetry is the isometry that preserves this equation. Indeed, it's not the symmetry that preserves H. We didn't start from that. We start from the asymmetry of the background metric.
So when you introduce the M, right? By introducing M, I believe that you didn't modify the system, but you modified the conservation law.
Yeah, it breaks the conservation.
I'm not sure whether the equation of original equation of motion after you change H can be set as a conservation law. So, right? So I was confused after that point.
So you mean after introducing this M term?
Right? And now you insert that H into your original equation and the Schrödinger equation form, right?
Oh, I see. I see what you mean. So
Is
you mean after introducing this M term, does it really indeed mean that the conservation of energy momentum is broken?
Right.
Yeah, I see your question. So indeed, so we cannot go back to this from the form of H because this form of H is determined from both the conservation and the constitutive equations. So we first try to find this H, and then we try to deform this to get this H. We didn't find this non-conservation directly going back from the form of H, but we modify this to try to find the form that is the same as this H. So that is
maybe you are introducing some kind of dissipation.
Oh, this is not dissipation. So as I said, this doesn't introduce
therefore, if you have a conservation, I mean then I mean the D anyway. Right, the right hand side, which was previously 0, is now no more 0. Therefore, what you wrote down is a non-conservation law.
Exactly.
That is what is going on, right? Right.
Yeah.
And then maybe you try to modify the system interpretation in order to interpret this as a sort of a conservation law.
You mean with QMQI?
Mm.
So up to this stage, we interpret this as a non-conservation of this energy momentum
Okay.
tensor.
Right.
But later, yeah, when we introduce QMQI, it's like
And-
a covariant.
Right.
So this covariant conservation looks like a non-conservation.
Right.
So there's some virtual forces.
So anyway, you want to try to interpret the resulting system still as a sort of a hydrodynamics.
Yeah, it's within the hydrodynamic limit, which means we can still find the dynamics of the system from the non-conservation equations. It only it's a little from the hydrodynamics. It's within the hydrodynamic limit, weakly broken.
Right. So anyway, I was a little bit confused after you talk about the so-called protecting symmetry. So-called, I was very sure.
Yeah, that's very condensed matter terminology. So in fact, it's just so. For example, if this gap could be opened by a certain perturbation, but not by other perturbations.
Yeah, I know that. I understand the condensed matter, but I didn't understand the terminology used in this context.
Mm-hmm. So it's like these two symmetries would forbid the mass term here and here in y and z directions. Because for this, if we have a I am here and I am here, the spectrum will look like this.
Right.
So it will become topologically trivial. So we need to forbid the m here. And to forbid the m here, we have to impose a symmetry. So with this symmetry, this term do not arise. It's like this. So we say that this is topological symmetry protected topologically non-trivial states.
All right. I understand your terminology more, but I still believe that whether you introduced IM, after you introduce IM, to me, it is not very sure what is the really modified, whether system is modified or.
When I introduce this IM, it could arise from this non-conservation of this delta T mu. If we break the conservation in this way, then the effective Hamiltonian of these two terms would arise in this way. So this means the energy density and the x direction momentum are not conserved, and also have to be in a special way to be non-conserved in this way.
All right. So, okay, thank you very much.
Thank you.
And we should stop now, right? So anyway, let's thanks to Ya-Wen again.
Late. Yeah, thank you.
And we have